Hey everybody, we're back talking more about discrete probability density functions, and I say more because the first one we looked at was the binomial theorem lesson from a couple of days ago. We have three more discrete probability functions to take a look at today. All right, so what is a probability density function? And we use this awkward acronym PDF, which usually is a file extension, but we mean it in statistics and probability for probability density function. And for a continuous function, the PDF is just the graph of the function. And the reason we call it probability density is the same reason that I have some area shaded underneath the curve. And how do we find area underneath a curve? Oh, an integral. So this is explaining some of the connections that we'll catch up with in statistics, but a continuous probability density function, right? The area under the curve corresponds to a probability that an event will occur. Okay. So an interval along the x-axis, is the probability that these events in here will occur, right? That area under the curve, the percentage, if the area under the curve is 100%, the percentage of the area under the curve that's shaded is the probability that an event happens. Okay, so that's continuous probability density functions. They're a little more understandable because we deal with graphs of functions all the time in algebra and calculus. For discrete probability density functions, we don't have a graph. We don't have area under the curve. But as we learned with the binomial theorem, we do have what's called a closed form expression for the formula, where on the right-hand side we have a rule. The function rule is just an algebraic expression. And if you tell me what outcome, k, the number of successes, so the outcome is k number of successes, and I have a way based on the rule to calculate that probability. And just like with the continuous functions, I can calculate a range of possibilities. What if k is between 3 and 7? Okay, so that's what we mean by a probability density function for a discrete function. Looking for this closed form algebraic setup that looks like a normal function that we would deal with. All right. And there's four that we're going to look at. We have already looked at binomial distributions, but we have geometric, which, by the way, is very familiar. It's a classic in mathematics, as well as the binomial distribution that you've probably seen before, and you maybe even know how to calculate the sum of a geometric series, these sorts of things. Hypergeometric. Now, I want you to think as we go through this relates to the partition lesson we had a couple lessons ago. And then negative binomial. Negative binomial is similar to the geometric, but these are the four that we use in this course. They tend to show up a lot in different probability problem-solving settings. All right, so let's go through these examples, and let's not just learn a formula and try to, do this pattern recognition, algorithm implementation kind of approach. Let's see if we can think of some of the problem-solving ideas for these distributions and understand why the pieces of the formula are there and what they're meant to do. Okay, so here we have a rolling a die, and so we've got a fair die, a six-sided die, and the success is a value that shows up on the die that's divisible by 3. So that's either the 3 or the 6. And we want to find the probability density function for this scenario and the probability that the first success occurs on the fourth roll of the dice. Okay, so we need a 3 or a 6, but the first 3 rolls don't produce either a 3 or a 6. And then the fourth roll is a success. Well, first of all, what's the actual probability we're talking about? Well, if we roll the die once, we have a 1/3 probability of getting either a 3 or a 6, right? Those are 2 of the 6 possibilities. Reduce that fraction to 1/3. So the probability that the first success is on the first roll is 1/3. But the probability that the first success is on the second roll is 2/3 times 1/3. Why? Well, there was a failure first, and then we had the success. So the failure is a 2/3 probability, and the success is a 1/3 probability. And then the second, if the first success happening on the third roll, third, I copy paste error, that should be an R and not an N. But the probability that the first success happens on the third roll is 2/3 squared, right? Because there are two failures, and then there's the success probability. Okay, and I have some typos on the slides I'm using, it appears. Sorry about that. Let me clear the marks and see if we can move on to do what? Well, let's put it in a chart form and see as we go down the chart if we can see the pattern, right? So the probability of having success on the first die roll is 1/3. On the second die roll, and notice this, 2/3 to the first power. And I know we don't normally write that, but in this chart, which is going to help us see the pattern, it helps to put that thing that we usually leave off, put it there. 2/3 to the first power times 1/3. We always have this power of 1/3 to finish. Why? Well, because that's the success criteria. The success criteria is that the first success happens on this X time, right? First, second, third, fourth, fifth, whatever X is. Okay, and the probability that the first success happens on the third die roll, notice that the power we raise the 2/3 to is 2. For the probability for 4, we raise it to 3. So the power that goes with the 2/3 is always 1 less than X. That's interesting. The 1/3 is stable there at the end. And so with all of that said, we have a nice way to write this closed form solution. So here we're using capital X as the event set, all the possible outcomes that can occur. And the probability that I get a specific X in that lowercase x in that set, right, is 2/3 to the X minus 1 times 1/3. And this is a classic geometric distribution. And the increasing pattern that we see as the powers increase, the exponents increase, is happening with the 2/3. And then we have a constant of 1/3 multiplied by that geometric pattern. Well, I guess the 1/3 is part of the geometric pattern. So again, this pattern should look a little bit familiar from things we've done prior to this in mathematics. So let's go ahead and put this in the terms. This is the formula, right? If you want to do it that way. So if P is the probability of success and Q is the probability of failure, which is 1 minus P, and N is the number of the trial on which we see the first success, right, then the probability of N being the place we see the first success is Q to the X minus 1 times P. Okay, so we can use this for a lot of different situations, and then all we have to change is the probability of success and the N that we're looking at. That doesn't change the formula, but again, evaluating the formula will be different depending on whatever N is meant to be in that problem. Okay, and the original question did ask about what's the probability that N equals 4, and we can just plug and chug in the formula from above to see the answer, right, if we plug in. And sorry about this, I did X equals 1 and N here, but those are supposed to be the same variable, so this should be N minus 1 up here. But if I take the 4 minus 1, I do have an exponent of 3. 2/3 to the third times 1/3, that is 2 cubed in the numerator, and 3 to the fourth power. 3 times 3 is 9, times 3 is 27, times 3 again is 81. So 8 over 81 is the correct value of that probability. Our second example is about the card game Hearts, okay? And we're I'm going to change the rules slightly. We're not going to play with the kitty. I know that some people play that way, but in a 4-player game with no kitty, we're going to deal each of 4 players a 13 card hand. So the event set is 1, 2, 3, up to 13. In other words, the question is how many hearts are going to be dealt into this 13 card hand? Okay. So they want the PDF and they want the probability of exactly 7 hearts in one starting hand. Now, as you know, if you've played the game, hearts are kind of a penalty that you play on the other players. So that's the malicious part of the fun game, hearts. And if you have 7 hearts, depending on how you like to play the game, that could be a really good thing. More hearts is better for you, not your opponents, but for you. Again, depending on how you like to play the game. All right, but what we want to remember is this is very much like the partitions. What are we doing? Well, we have this suit partition, right? And we have hearts, and we have spades, we have diamonds, and we have clubs, right? So we have 13 cards in each of these. So we have 13 cards here in the hearts part, right? So what are we doing? This value, and we're looking at, what's the probability of drawing 4 cards, 4 hearts into a 13 card hand? Well, there are 13 hearts to choose from, and we need 4, right? But the rest of the partition, the stuff that's not in the hearts, right? There's 39 cards there, and we're choosing the remaining 9 cards from there, right? 13 minus 4 is 9. So if we've chosen 4 cards that are hearts, we have to choose 9 cards that are not hearts. Over the total possible ways to pick a 13 card hand from 52 cards, this is the partition problem that we've already solved, or we've solved things similar to this, right? We're using the suit partition from a couple lessons ago. Okay. And notice that this should be a 5. Sorry about that. But the probability of drawing 5 hearts into one hand, 5 and 8. And notice this because this pattern holds for all of these types of scenarios. The 5 plus the 8 equals 13. The 13 plus 39 equals the 52. Why? Because those are the values in the partitions. And we saw that when we were working with partitions. This is a pattern that is going to be there in all of these. All right. So this is called the hypergeometric probability distribution. All right. And we have capital N, the total number of objects, and K is the number of objects that when we draw them, that counts as success. So in the one we just did, hearts, right? All 13 heart cards are successes when we draw them. So we have K equals 13 from the previous one. N is 52, the total number of cards we can draw. Okay, and the probability that lowercase k, successful draws, out of lowercase n, total draws. Well, how many draws am I making? Well, in a poker hand, it's 5. N is 5. In this particular kind of game, like with spades or hearts or bridge, N is 13. That's how many cards you're getting into your hand. And then K is the number of those that are success. Okay, and in this criteria, hearts was the success. And this is the PDF for a general hypergeometric probability density function. Okay. Now, this is why I say that the problem-solving portion is good to remember. Why? Well, it's the formulas get a little complicated, and you have to remember exactly what all the letters mean, and the uppercase is a little different than the lowercase and what they in terms of meanings. Okay, so that's why I suggest that we focus a lot on the probability features, the problem-solving features, so we know what this is actually about. So, example 3 is strikers who score. This is soccer. And the question says, over the past 10 seasons, Stina, who is a world-class striker, converts on 20% of her shots. Against today's opponents, the coaches estimate they will need a hat trick from Stina. That's 3 goals, if you're not familiar with that language from soccer. And what is the probability that if they get her set up 8 times that she scores her third goal on the 8th play? Okay, so a couple of things to notice here, right? We have a fixed probability of success, a fixed number of trials, sort of, right? But the success criteria isn't just scoring a goal, it's scoring 3 goals, right? We have a multiple goal success criteria. Again, we don't know this for sure, but we think she's going to need to score 3 to help her team win. And that if she only scores 1 or 2, that may not be enough for the win. So if that's true, the success is not just scoring a goal or scoring 2 goals. The success is scoring 3 goals. And again, there's a limited amount of times they're going to be able to get her set up. And you know how this is because this happens in more American sports like the NFL and the NBA. Again, they do try to set up their superstars, but the defense has a say in it too. So they can't always get the plays set up with their superstars able to make the plays as often as they want to. Okay, so we're going to keep doing the same thing over and over and have the multiple success criteria achieved on a specific number. Okay, on a specific number. So this is like the geometric pattern, except the geometric pattern just had a single thing that was our success. Here we have a multiple success event criteria. All right, so let's just look at this in the situation that we're finding the probability that she scores the third goal on her 5th attempt. Why? Well, it's just fewer letters in the pattern, all right? So that could happen if there was a failure and then success, success, success. Or that could happen if there was success, 2 failures, a success, and then a success. And notice that the last letter in this 5-letter sequence is always red, and I did that on purpose. Why? Because it has to be a success. Why? Because if the success criteria is the third success, right? The third goal. Okay. So the last event, if it's going to happen on the 5th attempt, the last event has to be an S. So what are we doing? That means that we're permuting 2 S's and 2 F's into 4 slots. And I'm not saying that this is all the possible patterns, but it's some of them. Just to show you, we're permuting into 4 slots, we're permuting 2 S's. That's going to be the piece that relates to the formula that we see right here. Okay, so what's going on here? 4 choose 2, right? This is the number of successes that we have to have in the first 4 slots, right? So 4 choose 2. And then here's one of the failures. Here's one of the failures. This tracks really well with the top one here, right? Failure, failure, success, success, success. Now, I know that we could use powers, and we generally do, but I expanded it and wrote it out long form. So you'd see that all the pieces that we talked about on the previous slide are here, right? 4 choose 2 is doing what? It's all the different ways we can permute all the different combinations of 2 S's and 2 F's in the first 4 slots, right? That's the 4 choose 2. And then these probabilities are fixed. No matter whether the F is over here, there has to be 2 failures, right? So the 4/5 has to be in there twice, and there has to be 2 successes. So the 1/5 is in there twice. And then the final success achieved, right? And of course, as you're suspecting is true, it will be true, I have just enough room to write that out for you the way we would normally write it, right? We do write 4 choose 2. And notice that we've seen this kind of pattern before. The probability of failure raised to the number of failures power, and the probability of successes raised to the number of successes power. All right. And notice that this is n minus 1. If this value here, 5, is the n, then n minus 1, choose 2. Why? Because there always has to be 2 successes. Why? Well, because the third success is the criteria, that the overall success criteria. All right. So the negative binomial distribution is similar to the geometric distribution, except the geometric has a single success criteria. The negative binomial has a multiple success uh, criteria, right? So if lowercase n represents the number of trials and k indicates the number of successes needed to achieve that overall success, p is the probability of success, q is the probability of failure. And again, this difference between x and n, I apologize for. So think of this as the probability of n being the last trial, right? If this was an n here, if n represents the number of the last trial needed to achieve overall success, then the closed form PDF is n minus 1 over k minus 1 times p, the success power raised to k, and the failure power raised to n minus k. On the other one, I had said that it always equals 2. Okay, notice that it is fixed for each problem, but the k could be different. In other words, we could say, well, we need Stina to score 2 goals. Then our success criteria is the second goal scored. Or we need her to score 4 goals in a game. That would be a lot for anybody. But then the k equals 4. So that bottom number in the choose notation is fixed, but it's fixed for the problem, and it changes depending on the problem. By the way, as we clear this out, I do want to mention that I didn't just pick the name Stina out of a hat. The most recent, a week ago, we had the Champions League final for 2025. The Women's Champions League was decided on a goal scored by Arsenal's Stina Blackstenius. Okay, so that's where the name comes from. The example question is a tribute to that exciting game, and that only had 1 goal in it, and it was scored by Stina. And with the football note aside, the soccer note aside, that's an example of each of these. But what we have is we have a worked example section where we can go through in our notebook. So our notebook covers all of the distributions and the closed form, the general formulas for the closed form functions, PDFs. Okay? And then they give us some examples. And the first thing we've got to do in our notebook is have the combinations formula. So I put that in the notebook. And then look, they say, okay, Texas Hold'em. Here's our example, Texas Hold'em. And in Texas Hold'em, at the beginning, players are dealt 2 cards. Okay? And the term pocket pair just means that the 2 cards have the same value, like Jack, Jack. Okay? And what is the probability that he or she sits down at the new poker table, and the first pocket pair that he or she sees is dealt to him on the 5th hand, dealt to him or her on the 5th hand? What's that probability? Okay. Well, first of all, what's the probability of just getting a pocket pair to start with? That's where we need to start, right? So let's think about this, right? So we have 13 values, and we're going to choose a single one of those 13 values so that our 2 cards have the same value. Then from the 4 cards, we're going to choose 2, right? We have to have 2 of that value to have our pocket pair. And how many values are possible? Sorry, I need a division symbol there. The number of values possible is 52, choose 2. Okay, and I'm going to suggest that that's just 1/17. How did I know that? Well, let me run some quick math for you. The first thing I'm going to say is that 13 choose 1 is 13, and 6 choose 1 is 6. Any, a number, a positive integer, comma 1 is just that number. And then this combin 4 choose 2, we use it a lot. It turns out that that's 6, and I'll just show that to you. And it turns out that 52 choose 2 is 1326, I believe. Yep. Even though R has a little bit of trouble with the rounding. It is, in fact, 1326. The last thing I'm going to try to convince you of is that 6 times 13 divides evenly into 1326. Okay, so let's do 1326 divided by 13 times 6, which I believe is 78. But yes, there it is. This is how I knew that this was 1/17th, because if you write those terms out and you know what they mean in terms of factorials and start canceling the factorials, and you get to 1/17th very quickly. All right. So the probability of success, I'll just put it here as 1/17th and leave it at that. I'm going to delete this. Okay. Why do I want that? Well, because I'm going to write this formula now, and I want to use 1/17th than trying to use this decimal approximation. This is an approximation. This is exact. And this is a whole lot easier to type in, right? So now how am I going to do this? Well, there are 5 hands, and the first 4 are failures, right? So what do I have? Let's see. So the probability, and I'll just put _5. So the probability that the first success happens on the 5th one, what do I have? Sorry, 16/17. Why? Because I have 4 failures. So I have 6/17 raised to the number of failures power times the success probability raised to the number of successes power. And again, if I evaluate that, it'll evaluate it and store it. But if I want to actually see what's in that variable, what's been assigned in that variable, there you go. That's the correct probability. And if you'll look back at the geometric PDF, that's the right format. Okay, so let me get rid of those stray marks. Oil wells, and this is the classic negative binomial. You'll see this in almost any probability class you look at. They do the oil wells example. Why? Because it's a classic one and it happens, right? So the company buys an undeveloped oil field. Now they've done their assays and they think there's oil there to be gotten. But there's still a chance of success and a chance of failure for each of the wells that they drill. So they know there's oil around here somewhere, but it's hit or miss whether or not they actually get the wells to work out. So the company has enough funds that they can drill 7 oil wells and keep them producing long enough to get deep to see if they're going to strike oil. But to turn a profit, right? That's the problem. They've got money involved in purchasing the oil field or buying the rights to drill in that oil field. And they've got the money, they've got to purchase the equipment and the oil wells, then they have to actually drill it. You know, so there's a lot of investment that they've put in. And if all 7 wells are dry, they're going to lose a lot of money. But their profit point is 3 of those wells striking oil. So they're saying, okay, well, what's the probability that the 3rd success happens on the 7th drilled well? Okay. So we're lucky here because we know our probability of success, right? Our probability of success is 0.035, and therefore we know that Q equals 0.065, right? So I'm going to hashtag that, comment that out, but, right, the probabilities. Okay, well, we know that. And then what are we doing? Well, let's look at some patterns. Why? Well, okay, so we have 7. And again, what we have 1, 2, 3, 4, 5, 6, and then success. Okay, why am I doing it that way? Well, because we have 6 wells, and distributed among these 6 wells, 2 of them have to strike oil so that I can have the 3rd success happen on the 7th well. Okay, so what's going on in here? That's a 6 choose 2. right? That's a 6 choose 2, so combin 6 choose 2 times what? Well, if there's 7 wells and 3 successes, there must be 4 failures. So, sorry, I'm taking the 0.065, that's the probability of failure raised to the number of failures power times the probability of success raised to the number of successes power. And again, it helps to remember, yeah, there were 2 successes in here, but then there's the success at the end that we're counting. So there's a 2 plus the 1, right, to give me the 3. And I'm sorry I have typed that symbol incorrectly there. It's correct. And I misspelled my function name. There we go. And they have about an 11.5% chance of drilling 7 wells and having exactly 3 successes, with a 3rd success happening on the 7th. Now, remember that they're still successful if the 3rd success happens on the 6th attempt, right? It would just change some values in here, right? Because if we have 6 attempts, we have 3 failures, 3 successes, and we have to assort the 2. We have to arrange the 2 successes into the first 5 slots. So notice that it's not 11.5% chance of overall success. It's 11.5% chance of this particular success, where the 3rd successful well strikes oil on the 7th attempt. Here, this is on the 6th attempt. And again, they could be really lucky. And it could happen on the 5th attempt or 4th attempt or even the 3rd attempt if they were extremely lucky, right? So again, we can use this pattern to do a summation if we need to. All right. Card game spades. So we have 13 cards that are being dealt to us. What is the probability that a player's dealt spades? And if you've never played this game, spades is the trump suit, always. And so spades are great. They beat other cards. They're very powerful cards. And if you get 7 spades in the game of spades, you've got a great hand. It helps if they're not all, young enough that they can't go to school. But yeah, if some of them are old enough to go to school, you have a great hand, right? So what's going on here? Well, we have this partition, okay? And notice that we aren't going to do 4 choose 1. Why? Well, we aren't going to use the suit partition here. Why? Because the suit is already specified. We don't have to do 4 choose 1 to find which suit the cards are going to come from. We know these cards have to come from the spade suit. Okay, and there are 13 cards in the spade suit. And what are we doing? We're choosing, 7 of them. Okay? But then the rest of the cards have to come. From where? Well, from the other values that are not in the spade suit, of which there are 39. Okay? So there's 13 spades, and so there's 39 non-spades. We're going to choose 7 of the cards that go into our hand from the spade suit, and then 6 from anywhere else. And we're going to divide by what? We're going to divide by 52, choose 13, right? Whoa, holy smokes, that's slightly less than 1%. That's like 0.88%. So not very likely, which again, it's a great hand. And that's why it's a great hand. It's very, probability-wise, it's very unlikely. Okay, and then what happens? Oh, we're dealt 7 or more spades. What's the probability of being dealt 7 or more spades? Okay. Well, for the moment, let's start here. And what do? We do a for loop. Okay. And as we saw before, we'll use tab as our collection vector. It tabulates. We're going to store the probability of 7 spades, the probability of exactly 8 spades, the probability of exactly 9 spades. We're going to go through the for loop and calculate all of those things, store them in the tab or tabulation vector, and then we're going to sum them up after the for loop has finished running. And where does the for loop start? It starts at 7 and it goes to 13. And this is the part that's doing that. It starts at low and it goes to high. Okay, remember the curly brackets tell it what to do each time. That's the thing that's happening. And notice, right, we have the same combinations that we did above. 13 choose T. Well, T is starting at low, right? T is right here, starting at low. So 13 choose T, combin, 39 choose 13 minus T. The other, our hand has 13 cards in it, so we have to draw the other 13 minus T cards. Over 52 choose 13. So it's the same combination we did above, but it's stacked in this for loop and stored in the tabulation vector under K. This K equals K plus 1 is making the assignment work correctly in the tab vector so that we can sum them up. It's working. Otherwise, if we don't do this, it can we can have the wrong index, and then the tabulation vector doesn't work properly, and we can't sum it. So the K equals K plus 1 just straightens some things out for us. It took me a second to figure that out myself. And what do? We run it, and we find out that the chance of success here is right around 10%, 1%, sorry, 1%. And also always remember that it's stored the tab vector, the tabulation vector, and I can print that out too. And here you can see all the values that it calculated. And this, if you'll recall, is the n equals 7, and it matches the value we had right up above. And this is n equals 8, and n equals 9, 10, 11, 12, and here's the probability of 13 spades. And notice that these probabilities keep getting smaller and smaller because as the number of spades gets higher and higher, it's probability speaking, it's much less likely to happen. So this value isn't all that much bigger than the probability of getting 7. Why? Well, the rest of these guys are just infinitesimally small. They get smaller and smaller and smaller down to infinitesimally small. All right. But again, I'm trying to show you the problem-solving features that lead to us making the choices that we're making. That's going to make you more successful if you can focus on that sort of thing. All right, good luck with this and good luck with the homework problems, the exercises, and I'll be back soon to talk about expected value. Have a great day.